Any question? Alright, today we are going to cover some more circuit families. Before we have already introduced static CMOS, which is the most popular circuit family. We also cover patch transistor circuit family, okay, with even smaller chip area. But we still have some more circuit families. So some brief review on basic CMOS circuit. Remember that we mentioned it before. For static CMOS, each MOS transistor is a electrically controlled switch, and the voltage and gate control the path from source to drain, on or off, depending on your gate terminal. And for NMOS transistor, when gate is high, then it's on. For PMOS transistor, when gate terminal is 0, then it's on. So we have already covered that. So a typical CMOS, static CMOS gate, the inverter, okay, we've already introduced that. And also the circuit for the inverter, that's the cross-section view for the circuit, okay. The PMOS transistor, and NMOS transistor. That's the layout. Okay, we've seen that before. And I mentioned for a complementary CMOS gate, there are two neighbors. One is product neighbor, close to the VDD. The other one is product neighbor with NMOS transistor, close to the ground. And depending on your input value, you produce the output value. So typically it should be 0 or 1. But for some circuit, it can be floating state, which is Z, no signal value at all. And it should not be allowed. You have a don't know, unknown, or cross bar, meaning if both product are off, they compete with each other. This one trying to put up to 1, this guy trying to put up to 0, and 0 and 1 signal conflict in the output. That should not be allowed. Okay? For static CMOS. Okay, I'm going to skip, we have already covered these pages. Okay? Now, actually before static CMOS circuit, the pseudo NMOS even appeared earlier than static CMOS. In the old days, NMOS processes had no PMOS transistor, only NMOS transistor. Okay, in that time period, instead we try to use product transistor that is always on. What do I mean? Okay, look at this circuit here. There's a PMOS transistor here, NMOS transistor here, and the input from low to high, from high to low, the input signal. VR is output signal. This is an inverter circuit, okay, with NMOS transistor. And this PMOS transistor is actually always on. You connect to ground here. But we treat that PMOS transistor as a resistor, actually. It's like a resistor. Because that kind of transistor provides you some resistance, and when you apply some voltage, you're going to have a current going through. So imagine that this is a resistor. So when the input is low, when input is low, NMOS transistor is off, not connected. 0, and it's off. So there's no current goes from VDD to ground. There's no current at all, or almost no current. When there's almost no current, then the voltage drop is going to be nearly zero, right? Can you repeat it? When input is zero, MO transistor is off, it's cut off. So there's no current, or almost no current, going through from VDD to ground in the past. Since there's no current going through the resistor, there's no voltage drop. You remember that? The equation I multiplied by R. That's the voltage, right? 电流乘上电流就是电压压价 Because I equal to 0, so there's almost no voltage drop. Because there's no voltage drop, you will get 1 in output. Is that right? Okay. On the other hand, if the input is 1, when input is 1, then MO transistor is on. So there's a current. There's a significant volume of current going from VDD to ground. And because this is on, it's almost like a wire, right? Almost like a wire. So there's no voltage drop, almost no voltage drop. All the current goes through the resistor. There's a significant voltage drop here. And you're going to get 0 in output.当 MO transistor是导通的时候，电流足够大，所以通过电阻值有足够大的压降。这边几乎没有压降，因为那是 wire. It's just like wire, so there's almost no resistance, so there's almost no voltage drop. So that's why if you ground, you get 0, almost close to the ground in terms of voltage. All the voltage drop will be here because of some volume of the current going through the resistor. So this is exactly inverter, right? It's just like inverter. It's going to be like it will be similar to this circuit. But now in here, we use PMOS transistor always on. Okay? We call that pseudo NMOS circuit family. Pseudo NMOS. However, for this kind of pseudo NMOS to be working, there are some requirements. What are the requirements here? Requirement is that the ratio of the PMOS transistor and NMOS transistor is important, it's critical. We call that ratio issue. The ratio between channel and length of the transistor. You have to adjust your channel length and channel width such that it's going to be working. Basically, based on the circuit simulation, we should try to make PMOS transistor about 1/4 effective strength of pull-down network. This guy should be 1/4 effective strength of pull-down network. So the circuit simulation try to simulate with different P value. P is the channel length, channel width. 2 is the channel length, minimum channel length, the channel width. So it's a wide PMOS transistor. And how about P? The PMOS transistor, it could be from here we have 4, 14, 24 different curve. Ideally, we hope that if 1.8 is the full voltage, ideally it should be like this. This is the ideal waveform we like. However, it cannot be ideal. So we try to have some kind of waveform that's close to the ideal waveform. 0.9 is the middle. Okay. We hope that your curve should be sitting in the middle, meaning when we increase the voltage for the input from 0, 0.3, 0.6, 0.9 is about crossing the middle value between 0 and 1. And your output will be changed rapidly from high to low. That's the idea. Ideally, we hope that to like this, but it's impossible. So try to close to the ideal waveform that should look like this. So can you tell me what should be the p-value? If it should be 1/4 effect strength, then what's the ideal value for p? How many lambda for PMOS transistor for channel width? Channel length always 2, the minimum channel length. And MOS transistor sitting in the channel width. How about P? What should be the value here? Suppose MOS transistor and PMOS transistor, MOS transistor and PMOS transistor have the same mobility. Electron and hole have the same mobility. Then, for 1/4, it should be 4. However, we know that PMOS transistor is weaker than MOS transistor because of mobility. So it should be what? It should be double of 4. That should be A lambda. And we'll make the PMOS transistor about 1/4 effective strength for that network. For inverter, okay. For the other gate, like NAND gate, NOR gate, that's a different story. But for inverter, that should be 8/2. That will give you the ideal waveform, close to the ideal waveform for the inverter. Any question? And the reason why the PMOS transistor was on is we try to make that component not real conductor and not real insulator. It's something in between. Okay, so it's that like a transistor, although it's not really linear transistor, linear resistor, but the behavior would be something like that resistor. So 8/2 will give you something that not really conductive, but not really insulator. And that's why we choose 8/2. Okay. Any question? But actually, nowadays, pseudo MMOS is not a popular state CMOS. State CMOS is still the best technology for the circuit family. Okay? Then before CMOS circuit era. Okay? But still, there's still some benefit using pseudo MMOS compared to state CMOS. What's the benefit? If you compare slow MMOS versus steady CMOS, we claim that CMOS is actually better, actually much better. However, there's still some advantage for slow MMOS. What is that? Well, power consumption, steady CMOS is the best, much better than slow MMOS. Because slow MMOS, this guy, PMOS transistor is always on. Not full on, but semi-on. Because of that, there's always a current going through. Always. Which is bad. Because when you have current going through, always, it consumes power. Which is bad. For steady CMOS, like this one, inverter, only when you are switching from low to high, or high to low. Only when you are switching the two edges. Only when you are switching, the MMOS transistor and PMOS transistor will enter the transition state. Let's draw the waveform. Input and output. The input from low to high, from high to low. The output something like that. And when you are switching, you consume some power. When you are not switching, there's almost no power consumption. Why is that? When A is 0, then this is off. It's off. So there's no current from VDD to ground, right? Almost no current. This is off. Almost no current from VDD to ground. So there's almost no current, so there's almost no power consumption. Remember power consumption? I square R, right? The physics equation. That's power consumption, or IV. Okay. That's power consumption. And when A is 1, on the other hand, when A is 1, so this one connects, this one is off. Again, almost no current going from VDD to ground. Because in the past, it's off, it's disconnected. So there's almost no, not really totally disconnected, but there's almost no current going through. Such that the I square R also very, very low, or even almost no current or no power consumption at all. That's when you have steady 0 or 1 for the input. However, when you are switching, the input in here, then it's semi-on. At that moment, there's a current for me to run. When A is in between, not 0, not 1, but in between, about 1/2, midway, from low to high or high to low, then PMOS transistor and MMOS transistor is semi-on. Not really on, but in between. At that moment, you have a current from VDD to ground. Okay? So that's the power consumption for steady state mode when you are switching, when you're in transition state. But that time period is very short, not very long. Only in this time period, you have power consumption for the inverter. However, that's not the case for solar MOS. For solar MOS, PMOS transistor is always on. It's always a current for VDD to run. You are always consuming power. That's why steady state mode is much better in terms of power consumption compared to the solar MOS. That's why people nowadays simply abandon solar MOS circuit family. Okay. But there's still some advantage for solar MOS. What is that? Can you try to imagine what could be the advantage? Although overall it's not very good compared to steady state mode. Steady state mode is much better, but still it has some small advantage compared to steady state mode. What could be that? This is for inverter. How about NOR gate? For NOR gate, there are two MOS transistors. This is NOR gate, and still only one PMOS transistor. Even though you have a lot of circuit in the product network, there's also only one PMOS transistor in the top. So you can see that from chip area, it could be smaller. Alright? For inverter, no, there's no such advantage. But for a compound gate or for like 3 input, NAND gate, NOR gate, this kind of thing, you're going to have the same product network with the steady state mode. But for product network, you need only one PMOS transistor. We still need 3 or even more transistors in the product network for steady state mode. So from chip area point of view, solar MOS could be better. It could be smaller. Okay, that's the only advantage compared with steady state mode. But nowadays, power consumption is the most important issue actually. So that's why CMOS transistor become much more popular nowadays. Any question? Another family, dynamic logic. Dynamic logic is not steady state mode. It's dynamic, not steady. Dynamic gate uses the clock PMOS product. This is steady state mode inverter, okay? And this is pseudo MOS. Okay? And this is dynamic inverter. And the idea is that, again, just like pseudo MOS, there's a PMOS transistor at the top. And then the MOS transistor here, this is an inverter circuit. And the reason why we call that dynamic circuit is that we are trying to utilize the parasitic capacitance. Implicitly, there is a capacitor at the output. It's coming from the transistor layout. Anyway, not a real capacitor, but your layout actually has capacitance. So assume that there's a capacitor here, and 5 is the clock signal, A is the input, Y is going to be the inverted value of the input A. And there are 2 phases for the dynamic logic, 2 modes or 2 phases, pre-charge and evaluate. depends on your file, your clock signal. When the clock signal is low, it's pre-charge phase, pre-charge mode. When clock signal is high, it enters evaluate phase, evaluate stage. And then again, pre-charge, evaluate, pre-charge, evaluate, so on and so forth. So how does it move? When A input or during pre-charge phase, okay, the PMOS transistor is on, right? When clock is low, here, low, so PMOS transistor is on. When PMOS is on, there's a current to charge the capacitor. There's going to be a current from the VDD charge the capacitor such that you're going to accumulate more and more charge. So the output goes up, will go to accumulate more and more capacitor, more and more charge, and your voltage is going to go higher and higher and higher until it reaches signal 1. Okay? So you get Y output 1. Okay? You're getting signal 1 during the charge phase. After that, the clock signal goes up, goes to high. You enter evaluate phase. And then what? When the clock signal is high, then PMOS transistor will be off. Right? When signal is 1, clock signal is 1, PMOS is off. When it is off, whether or not the charge of the capacitor, the charge will depend on your MOS transistor. Okay, let me repeat it. Clock signal is 0. PMOS is on. So there is a current from VDD toward the ground going through the capacitor. So you try to charge the capacitor, try to accumulate more and more positive and negative charge on the capacitor until it reaches signal 1 for voltage. It will have enough time to charge it. Why actually it will have some kind of waveform like this? Okay. In the beginning, the current actually loud, so charge really fast. But as you accumulate more and more charge here, more and more voltage here, the current becomes lower and lower and lower, so the speed becomes slow, reaching, try to reach the saturation point. But anyway, eventually you will get signal 1 for voltage. After that, clock signal becomes 1. You try to evaluate the value of the circuit. So it depends on A value, either 0 or 1. If A is 0, the MOS is off. Then your output 1 will keep the value high. It's still high. Because there's no current to discharge the capacitor. You keep high. However, if signal input is 1, then MOS is on. When MOS is on, there's going to be a current from the capacitor to the ground. There's a path. You will discharge. The charge will follow the current going through the MOS transistor to the ground and then disappear. So the voltage at Y will become from high to low. So it will go high, keep high or go low, depending on your A input. When A input 0, M alternate is off. You keep high here. When A is 1, M is on, then there's a current from the capacitor to the ground, carrying out, take away your charge on the capacitor. And then with smaller and smaller, little and less and less charge on the capacitor, your voltage on the capacitor becomes lower, 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 eventually becomes 0. So the output becomes 1 or 0, depending on your A input. When A input is 1, you get 0. When A input is 0, you get 1. So that's exactly 1. That's exactly inverter behavior. Okay, let me repeat it. It's going to be a little bit complex. Let me try to repeat it. This is a dynamic logic. Okay, so you can see that it's not the same with the state CMOS. Okay, not the same. There's a PMOS transistor, just like pseudo MOS, but this pseudo MOS, this PMOS transistor is with the cross signal with the terminal voltage. And there's a two phases, two stages, pre-charge stage and evaluate stage. During pre-charge stage, cross signal is low, right? It's 0. So PMOS transistor is on. It's on. So there's a current from VDD toward the ground. There's a path which has a current going through. And that current will be charging the capacitor to accumulate more and more electron and hole on the capacitor. So this voltage will become higher and higher and higher. Eventually it will be reaching high voltage here. And at the beginning it is quicker, but then slower and slower.
老师，
Yeah.
这个时候如果 A 是1的话，它会直接流下去吗？电流。
Okay, good question. The question is that what if A is 1? Then M alternator is also on. Okay, so that circuit actually has some deficiency. There are some problem with that circuit. We are going to remedy that. We are going to correct that problem. 它这个的确有点小问题，因为如果 A 是1的时候，这是 on 的，它也会可能往这边走，但是这个问题实际上是可以解决的。如果这样设计其实有问题的，是不太理想的。我们要再来修正它，我们要再解决问题。So just ignore that the A value. Assume that the PMOS transistor is off. Simply assume that it's off during the pre-charge phase. So as I mentioned, that just for we are doing that again. During the pre-charge phase, cross signal is low, so PMOS transistor is on. Just assume that this is off, okay? So there's a current from VDD to the ground. The current goes through in a path. So the current tries to charge the capacitor with more and more positive and negative charge on the capacitor. So we're giving higher and higher voltage on that capacitor, which is the signal value, the voltage on the output, right? So it goes high. In the beginning, faster, and then slower and slower, reaching the high voltage. After that, we enter the evaluate phase. In the evaluate phase, the cross signal becomes 1. And then PMOS transistor is off. When PMOS is turned on, then it depends on your input A value. The A value will determine whether or not the charge will be discharged, will be disappearing. Because if A is high in 1, then MOS transitor is on. Pure state is off. So there's a current because the voltage drop, from here to ground. You have voltage here, high voltage, and here is ground. So there's a current, right? From here to here. It will take away the charge of the capacitor with less and less charge, less and less electron hole on the capacitor, so you get low and low voltage at the output. And at the beginning, it's very fast, but and then slow and slow and slow. Okay, like this. The beginning is very steep, very fast, because enough voltage difference. The current higher. But when you take away the charge on the capacitor, your voltage becomes lower and lower. When the voltage is lower, the current is smaller and smaller. So the speed, taking away the charge, becomes slower and slower. That's why the beginning is very steep and then becoming slower and slower when you reach the low voltage. Eventually, they are all gone, and there's no voltage at all. You get zero at the output. So that's exactly inverter, right? Input A is 1, you get 0. Input A is 0, you get high. Because if A is 0, PMOS transitor is off also. So there's no current going away. Your current will be still there. Your charge will be still there. You still keep a lot of charge on the capacitor. You still get high voltage in output. So depending on your input A, you get high or low. And that's exactly inverter behavior. Right? Any question? Okay, now we are worried about the MOS transistor during the pre-charge phase. So a modified circuit should look like this. There's a foot MOS transistor at the bottom. In class signal, put it like that. That will solve the problem. Why? There's a product network still here. No product network. You have a PMOS transistor and MOS transistor connected to the class signal like this. If there's no MOS transistor at the bottom, it's unfolded like this. But to solve the problem with leakage, current leakage, you should have an MOS transistor at the bottom or at the foot. Another good inverter dynamic circuit is unfolded. The problem with the unfolded is that during the pre-charge phase, it's 0 and you current goes through. Now, how about 81? When 81 is also on. Both are on, so there's going to be current going here and going here. 它会造成分流，它既有电往这边流，又有电往这边流，在 pre-charge phase. This is not what we want. We 不喜欢那样 we don't like that. There's going to be two current, one runs through MOS transistor, one runs through capacitor. If A is on during pre-charge phase, which is not good, because that will make charging capacitor much slower. We hope that this should be cut off during pre-charge phase. That's why we have a full MO transistor here, because when the clock signal is low, 0 is going to be on, is going to be off during pre-charge phase, right? Okay? And during evaluate phase, clock signal will be 1, and now it's on, and it's going to be on. So the catalyst still can discharge it. So what I'm saying is that on the previous page, there's no MO transistor at the bottom here, unfortunately. We provide MO transistor at the bottom is a 40 diamond circuit, and that's a good circuit now. Because during pre-charge phase, it's going to be off. You can only charge the capacitor. During evaluate phase, it will be off. It will be on. So depending on your product level, the current will go through if this level is on. So you can take away the charge on the capacitor depending on your input. If input make the product level is on, then the current is charging the capacitor. If the input make the product level is off, not on, then you can keep that charge on the capacitor still in the value phase. So what if product level is on during pre-charge? That's the problem, that's the issue. Use serial evaluation transistor to prevent fire, to prevent that the two pads fighting with each other when you pre-charge the capacitor during pre-charge phase. Any question? So how does it compare with the static mode? We know that static mode is better than solar mode. How about dynamic circuit here? Anything better than static mode? We know that this level is actually the same circuit with the static mode in the product level. For product level, you need only one PMOS transistor, and you also need one MOS transistor at the bottom for the foot. How does it compare with the static mode? Still, in industry, static mode is the most popular circuit family. But in some specific area, in some specific application, people might use dynamic circuit. Why? How can it provide which is better than static mode? What specific purpose? Any opinion? Any answer? What could be the benefit for static for the dynamic circuit compared with the static mode? 有什么可能的好处会用它呢？ If there's no any benefit, then it will disappear in the world. It will disappear from the industry. However, some people still use dynamic circuit for specific application. What could be the benefit? Any opinion? 有没有可以想到的答案？什么样的情况之下，dynamic circuit 有可能会稍微好一点？ Could be better than static mode in some specific purpose.
They are smaller.
Smaller, okay, good answer. Well, yes, for inverter, no, it's not better, it's not smaller. But yes, if your circuit has quite a few transistors connected, just like super MO, you only need one PMOS and one MO. And this product level, the same product level. It could be smaller, yes. It could be smaller. What else? Okay, it could be faster. It could be faster than steady CMOS. Okay, actually, standard circuit is popular for high-speed circuit design. For typical circuit design, steady CMOS dominate the whole industry. However, for some high-speed circuit, people could use dynamic circuit. It's only at product level, and we know that product level with MOS transistor, for each MOS transistor, MOS is faster than PMOS transistor given the same size. Okay, and also we only use the product level when you in the value phase. There's no product level that could be the circuit bottleneck. Okay. So yeah, that's why we still need to learn designing dynamic circuit, because it can be applied, it can be used in high-speed circuit design in industry actually quite a lot. Okay, let's take a break.
在希望它有两个那个一个 P 一个 A 对不对？那所以你如果说 P 那边有超过2个垂直的话，它是就表示有垂直的，所以对小电路像什么 inverter 降力比较大便宜。可如果对一个比如说什么3音或者 N gate、N gate 或者 common gate， 那这个的确比较小。更何况我们在做 stage mode 的时候，常会把 P mode 垂直的试着去把它们宽度加宽，让它可以平衡它上中下降的速度，可这边都没有这么大，它这边所以这边通常来讲，这的确比较小。
然后你说比较快，是因为它只有多当内位。
对，就是说你在如果是 stage mode 的话，你要看它跟波浪，最慢它是你的那个电路的一个前景。那这个话只看 MOS transistor， 而一般如果同样大小的 MOS transistor， 电路的时候，它这边只有 MOS transistor， 一个 MOS transistor 本来就比 PMOS transistor 要大，如果同样大小的话，那所以我们如果这边去设计，我们刚刚再看还有别的版本的dynamic circuit， 这叫中央 circuit， 它就非常非常常用在一般产业界在做 high speed circuit design 的时候。
老师会拿它跟那个苏州那个比。
苏州 MOS 吗？苏州 MOS 是很慢的。所以是。苏州 MOS 不考虑，因为苏州 MOS 它
一方面光耗能就
一方面功率消耗的问题，一方面这边的速度不会太快。PMOS 纯粹的它你的那个它上次刻意把它的它做的有足够的阻抗，它不是一个非常容易导通的，它等同于是一个电子器一样。那所以这边的到氦的时候，本身这个上次是偏慢的，就是它的那个电路来讲的话，它速度其实还是没有像别的非信号或无线来的快。
所以这个是最不好。
现在几乎都没有在用了，除了少数那些像省面机，那有可能会用它。像一些 PLA 的电路你的 A plane O plane 有可能会使用到 Sway mode。 否则的话一般就是不用。
这张图我看不太懂，你可以教我。这张图。
他就说，就是说理想的情况下，它应该是要那个高电压到低电压的波应该要长这样。
哦，应该是红色那条。
对，理想的是要这样，但是就是他说大概都是怎么讲？这个要是这个的4分之一，
这个要是
就是怎么讲？因为就是要往理想上，所以越靠近这个越好，对吧？但是就是实际上大部分都是用就是差1/4倍。
哦，这是有什么这个？
对，就是这2个要差1/4倍，但是因为它是 PMOS，它的载值电动会比较慢，这导致就是假设说它电动会比它慢，就是比它慢2倍嘛，所以它要先把这个除以4之后，是16除以4是4嘛，它再乘分8。
今天不担心课都给你。今天一场的啊，直接就。不懂，这个不懂是吧？
都退赛啊。
对，都退赛，希望嘛，大概一点。